Just a real quick question. Yeah, so you said Taylor Kelly before. I didn't know if you were looking for Tyler Kelly or me, but we're both here.
Very good. All right, then you just answered my question. Then very good. Okay, I'll make sure that you're all on there. Yeah. All right. Thank you. All right. Let's see. So now let's go to the topics that we are discussing, right? And if you have any question, let me know. I'll put the slide that we are in. And you tell me, this is the last slide, we talked about it. But we talked about more than that, what we have here. All right? Everybody okay with it, right? Yeah, we talked the glyceraldehyde, precursor, we talked we talked we talked about so many things, right? Optically actant, digital configuration, etc., etc. All right? The next one, as you can see, the glyceraldehyde is a precursor of all those hexoses, all those saccharides or aldoses. So if this is a precursor means they start from there. That's basically the idea. Precursor meaning that most of them originated from that molecule. Many of them are naturally made, but definitely they can be synthesized from the glyceraldehyde. So the next one, how can you convert the glyceraldehyde, a triose, glyceraldehyde is a triose, into other saccharides. So that's basically we'll do it today. Okay, we'll do quite a few more, of course. So let's say glyceraldehyde looks like this, right? As you remember the structure, we talked about it, right? We have like this, and we have the C and H is a D configuration. All natural sugars are D configuration, we talked about, right? All natural sugars are D configuration. So that's a D-glyceraldehyde. Fine, that's basically our starting material. And let's see how we can convert the other saccharides from this. So that's a D-glyceraldehyde, all right? D-glyceraldehyde. Everybody okay, right? Aldehyde, all right? So that's a name. Please pardon me, that's a glyceraldehyde, D-glyceraldehyde. Now, D-glyceraldehyde, if it is treated with hydrogen cyanide is the reagent. This is in vitro synthesis. How we can convert from one triose to tetrose, pentose, and hexose. I'll show you the pathway. And so first is treated with reaction number 1 is treated with HCN. HCN dissociates into H plus and CN minus. So CN minus is the nucleophile. Remember, it's a nucleophile, and you have a nucleophilic center right here. C.1 carbonyl center. So it can attack on this way, on the back, or it can also attack at this from right here, so one from the back, one from the front. Okay, so there are two ways it can attack, because this is the nucleophilic center. Therefore, based on the attack from which side, you have two different molecules, or 50-50. So you'll have a CN, that's a CN, that CN will go there, and then you have a CH. Remember, that's a carbon number 1, right? That's a carbon number 1, 2, and carbon number 3. So it's attacking the carbon number 1 because it's a carbonyl center, nucleophilic center, and as it attacks, the hydroxyl group will be this side because they are attacking from the back, right? Attacking from right there. Hydroxyl group on the right hand side, and other carbon, that's a carbon number 1, in fact, by the way, and then you will have a carbon number 2 remains as it is, no change, all right, and the carbon number 3, no change either. All right, so this is the one molecule, 50%. Another 50% will have like this way. So you'll have the CN remains as it is, all right, we're writing in the top, and then we have a C, and then HO. So it is attacking from the back, right? Attacking from the back. Therefore, this hydroxyl group, if attacking from this side, hydroxyl group will the left hand side. It will flip. It will go to the other side, and that's the hydroxyl group. It's the carbon number 1, and C, and H, OH, and ultimately the other one remains the same, right? So you have the C1 carbon is opened up. So you had a triangular planar. Now this is a tetrahedral. As you can see, it's a tetrahedral, right? So they are cyanide derivative, and And now both molecules, they're 50-50 by the way, 50%, 50%. If you treat with a reaction number 2, the hydrolysis reaction with a weak acid, if you put the weak acid to it, then this CN group will be hydrolyzed and ammonia will be removed. NH3 will be gone. This ammonia coming from the nitrogen, all right? And this C will be converted to carboxylic acid. So we'll have a carboxylic acid like this, COOH, carboxylic acid, right? And then we'll have a 1, 2, right? 1, 2, and 3, right? So I'm just writing like this way. This is called line drawing. This line drawing is called Fischer projection formula. We'll come back later on the names, all right? So now we have a carbon number 1, 2, 3, right? So remember, you can have 1, 2, 3, 4. So you have a 1, 2, 3, and the 4. So that means we have a carbon number 3 remains the same. It was 2 before, now it's become 3, and OH, right? OH and H. So that's this molecule. So this molecule is converted to this, and the next molecule is this one, will be converted exactly the same way. You have a carboxylic group, OOH, and we can have a this 2 lines, right? These joints, that you see the joints, they are carbon, by the way, all right? This is a notation, not to write the same thing again and again, but you can write it if you want to. And you have the same, you have a OH, carbon number 3, remains the same configuration, and hydroxyl group is right here. So that's the difference there, right? They are stereoisomers, right? And like this, all right? Carbon 1, 2, 3, 4. And so difference between this one is the carbon number 2, right? Including carboxyl group. Now, this molecule, the third reaction, reaction number 3, is the reduction of the carboxylic group. Remember, aldehyde is oxidized to carboxylic group, and you can reduce it with the help of Na and ammonia. That's a mixture, right? Sodium and ammonia. It generates the electron, gives the electron. That electron will reduce this limited reduction. Carboxyl group will be converted to aldehyde group. Aldehyde is oxidized to carboxyl group. Now it will be converted back to aldehyde group. So basically what we have, you'll have a C, H, double bond O, right? Double bond O, aldehyde group, and the rest of the things remains the same, all right? So basically you have a H, OH. We're doing the first molecule first, right? That's the first molecule. That's the second. Doesn't matter which one is which, but they have a different name. As you can see, they're not the same molecule. They have a different orientation of the hydroxyl group. And CH2OH. Tell me if you have any questions. So this is the first molecule reduced to this. Plus, you can also have the same thing. This molecule number 2. Once again, the usually ratios are 50-50, and you can have like this and this, right? So CH2, OH, no change there. Only the change is carboxyl group is converted to aldehyde group with the reduction. Oxidation makes the aldehyde to carboxylic acid, and this is the reduction. It's reducing back to the structure. All right. So now you can see what happened. So you have a carbon number 1, 2, 3, and carbon number 4. Everything okay, right? 1, 2, 3, and 4. So if you look at the molecule number 1, the starting molecule, this aldehyde. By the way, they are all Ds. They are all D. Because they started from the D. So D-glyceraldehyde has a 3-carbon aldehyde group, HCOH, CH2OH. What happened here? You have a C double bond OH, C double bond OH, so that aldehyde group remains the same, right? And now the carbon number 1 become carbon number 2. Hydroxyl group this side, hydroxyl group other side. All right? So who can tell me what are these molecules? So we started with the trios or trios. What we end up with? Who can tell me what we end up with? What group of molecules are this? Yeah? Say it. Anyone? What type of molecule are these? Remember, we started with the trios. So trios, what's the next? What's the next?
Tetros.
Trios, the tetros, absolutely right. Tetra is a 4. Thank you. Yeah. And the name of this, so this is a tetros family. Yeah, that's right. So carbon number 3 converted to carbon number 4 because of the cyanide group and all those reactions. The first one is called D-trios, D-retros, and the second one is called D-trios. Everything okay? So write down the names, okay? The names are given as it is. And now, if we take D-retros and do the same thing, we can do the same thing also. We can separate them, and after separation, take this molecule and treat with the reaction number 1, 2, and 3. So first treated with hydrocyanide, hydrocyanic acid, HCN. Second, hydrolysis with a acidic solution, right? Acidic solution. And then third, the reduce with the sodium and ammonia mixture. So let's start with the trios, and we'll end up with the pentose, right? We're adding one carbon at a time, and we'll do this one also later on. First, let's do this one, and let's see what we can get. And what we'll get 2 molecules, of course, as usual. So HC, aldehyde group remains the same. Remember, right? Because that's basically generating. So yes.
So I have a question. So in the first molecule that you drew, the D-glyceraldehyde, there are 2 aldehydes, right? The one on the very top, the HC double bond O, and then the CH2OH, correct?
So C double bond OH, CHOH is a secondary alcohol, and CH2OH. Yeah.
Which one is the aldehyde that they're not all aldehydes, right?
Right here, carbon number 1.
Right,
So
okay.
If you take the whole molecule like this, the R group, RCH double bond O, aldehyde. Yeah.
Okay, and then the aldehyde doesn't come back until you get into the
End of the reaction 3. Third
right,
reaction. Yeah.
Okay. And then one more question. What are the arrows at the very beginning? Like, it's like linking the C back through.
HCN, hydrocyanide, HCN. H positive, CN negative. CN is the nucleophile attacking the nucleophilic center.
Okay, so are you just showing like where the elements are coming from?
When the O is coming, so basically once the CN attack from the back, it becomes O minus, and this H plus will add to it, become OH. Likewise, if CN attack from this side, hydroxyl group from the left, and H will be added from the H plus. Yeah.
Okay, thank you.
You're welcome. All right. So there's a first molecule like this, and then I'm going to draw the whole thing within a minute. I'm just doing the skeleton, and this is also second molecule. Remember, every time we take one molecule, we have 2, right? And why 2? Because of the nucleophilic attack, right? And it's opening up. So now, let's say first molecule, for example, let's say hydroxyl group on the right, OH, this is our base molecule. We started with this one, right? So H, CH2, OH, all right? That's a base. That's what we started with, right? OH, CH2OH, OH, CH2OH, all right? And then we'll come back to the next one, and this is the same thing. Remember, the base remains the same. That's the base structure remains the same, right? OH and OH, and H and H. So nothing happened, right? The base structure remains the same. 1, 2, 3, 1, 2, 3, or it go like this way: 2, 3, 4, 2, 3, 4, 2, 3, 4. Now this one will be converted to OH, right? That's what will happen. So therefore, you can have like this. You can have one hydroxyl group this side, and H on the left, and hydroxyl group on the left, and H on the right. So they are true stereoisomers, right? The configuration is different on the carbon number. So carbon number 1, 2, 3, 4, and 5. So now you got the pentoses. Remember, every time you do this reaction 1 to 3, you add one carbon, right? A carbon plus other derivatives of that group, right? Other aldehyde group, we are adding aldehyde group, and aldehyde group is become CHOH, all right? So this molecule, this is my cursor, so just pardon me. So this, all right, come on, all right. This is my cursor is kind of with something. So this is called D-ribose. First molecule that I put is called D-ribose. D-ribose. And you tell me what do you find the D-ribose? And this one is called D-arabinose. This is the name, huh? D-arabinose. D-arabinose. OS, you remember? OS is the sugar. So D-arabinose is this one. One hydroxyl group on the carbon number 2 on the left. One hydroxyl group on the right. Carbon number 2 on the right. Called D-ribose. Who can tell me where do you find the D-ribose? Anyone? Where do you find the D-ribose?
In our nucleic acids.
Which
In our
one?
DNA.
No, RNA. RNA. Yeah, it's found in RNA. RNA is a ribonucleic acid, right? So ribonucleic acid. Ribonucleic acid. Now, on this molecule, I'm writing like this. On this molecule, if C2, that's a C2, huh? If C2 is the H instead of hydrogen, instead of hydroxyl group, if C2 has the H this side, and other side is also H, like this. So basically what you have, C double bond H, C, H and H, not hydroxyl group, only H. That is known as deoxyribose. D means remove, oxygen, oxygen is removed, so deoxyribose. Now what do you find this one? How do you get this molecule? Yes?
DNA.
DNA. That's where the name came from, right? DNA stands for deoxyribonucleic acid. So ribonucleic acid is RNA. So this ribose is present in RNA, D-ribose, and D-deoxyribose present in DNA. So what's the difference between these two, ribose and deoxyribose? Please tell me in short, what's the difference between the D-ribose and deoxyribose?
I don't know. She's just like coffee.
Yeah?
No.
What's the difference between the D-ribose and deoxyribose?
No, she's not lying.
No, I mean, if she-
The carbon number 2. Yeah?
Oxygen.
The carbon number 2. You have to say carbon number 2. The configuration of the carbon number 2. Configuration means the arrangement of atoms or groups in a space. That's what configuration means. Configuration. So configuration of carbon number 2. In the carbon number 2 in the ribose has a hydroxyl group, and in carbon number 2 in deoxyribose has a hydrogen. Not oxygen is not there. That is correct. Oxygen is not there. So that's the difference between these two and these applications. So you must remember the structure of D-ribose and deoxyribose. It will be the test, one way or another. All right, sorry. No, sorry. Okay. Any question about this? We got the pentoses. These are all pentoses. The two of them are pentoses. And among the pentoses, most important one, D-ribose, and that is present in RNA, deoxyribose present in DNA. So that means, and the difference between these two molecules is the carbon configuration of carbon number 2. D-ribose has a carbon number 2 has a hydroxyl group on the right hand side, and deoxyribose has hydrogen. So now, tell me, the carbon number 2 in deoxyribose, is it optically active or optically inactive? Carbon center 2. Carbon center 2, C2. C2 center, that's the C2 center. This C2 center in ribose, it has 4 different groups or atoms, right? 1, 2, 3, 4, this side. So that is the optically active. How about deoxyribose? Is the carbon number 2 optically active or inactive? Yes? Carbon number 2 in deoxyribose. Carbon number 2 in deoxyribose. It looks like here, right here. Yes? It is optically active or optically inactive? Yeah? Carbon number 2. So it has both sides to hydrogen. One hydrogen this side, one hydrogen this side. So this carbon has the two same atoms. So this is a optically inactive. This carbon 2, the carbon 2 center is not a chiral center. And it has other, so if you have the D-ribose has 1, 2, 3 chiral centers, and deoxyribose has 2 chiral centers because it is hydrogen, 1 and 2. So once again, D-ribose has 3 chiral center, right? 3 chiral center. Everybody okay? If you have a question, please ask. 3 chiral center. All right, 3 chiral center, and deoxyribose has 2 chiral center. Tell me yes or no. If you have any question, please ask. For the test, all right?
I have a question.
Yeah.
Why is RNA? Why does it have not RNA? Why does ribose have 3 chiral centers if the carbon 2 also bonds with the carbon above it and the carbon below it? Doesn't that make it like 2 the same atoms?
So carbon number 1 is aldehyde group, right?
Yeah.
Then carbon number 2 has aldehyde group, hydroxyl group, hydrogen, and the rest of it. Rest of it is a different group. It's a big group.
Okay. So it's not counting like the immediate carbon. It's like more counting the.
You have to consider the whole thing. Yeah.
Okay.
Any other questions? Good point. All right. Let's move on then, right? Now,
Professor,
yes?
why does D-deoxyribose only have 2? I'm confused why 1 is 3, 1 is 2.
So the carbon number, the D-ribose has a 1 optically center right here. Look at my cursor, right? 1 right there, 1 there, and 1 there. Yes or no?
Yes.
Okay. Now replace this with the hydrogen. This oxygen is gone. If the oxygen is gone, then what do you have here? Carbon number 2. 2 hydrogen. Yes or no?
Yes.
So if you 2 hydrogen, remember the definition of a chiral center, 4 different groups or atoms must be different. Now you have a 2 hydrogen. So therefore, this C2 is not a chiral center anymore. Yes?
Okay, thank you.
Yeah. All right, let's take the arabinose. We'll take the D-arabinose and we'll do the same reaction. 1, 2, and 3. So as you do, we'll get 2 molecules, right? That's basically we're doing it. We're getting 2 molecules. And let's see what are the 2 molecules. 1 molecule is right here. HC double bond O, and the lines. Carbon number 1, 2, 3, 4. 1, 2, 3, 4, and 5. And the last one is CH2OH, the 6 carbon. All right?
I have a question.
Yeah.
Okay, so I'm just looking at all of the figures that you made. So are you saying that the dirose goes and they transform into dirose?
D-ribose and deoxyribose, yeah.
So if this is just like how it transforms into other.
State again. What's the last
So
part?
so are you saying that D-ribose turns into D-ribose?
D-ribose. This is the D-ribose, and this is the deoxyribose. So D-ribose has the carbon number of hydroxyl group, when deoxyribose oxygen is gone, it is a hydrogen. It's called deoxy. D means remove, oxygen remove. So oxygen is removed. That's and it's a ribose backbone. So it's called deoxyribose. Yeah, deoxyribose.
Okay, thank you.
You're welcome. So now we've got the arabinols, and we've got the reaction 1, 2, and 3. We've got 2 molecules. All right. Draw the 2 molecules. Very important. They're all important, of course. So OH. I'm writing the base, and then, sorry, my cursor again. So come on, please. Hydroxyl group here. All right. Look at the D-arabinose structure. Base remains the same. Base is not changing. So that's the hydroxyl group. Hydroxyl group, H group, HO, HO, and the H. All right. That's a one side, and that's a base, right? Let's say 1, 2, 3, 4, 5. I need one more carbon here. Right here. All right, I'll come back to that one. So remember, it is a 5 carbon, right? Aldehyde group 1, 2, 3, 4. 2, 3, 4. 2, 3, 4, 5, and 6, 5. They remain the same. Remains the same. So let's go to the base structure. OH, H, H, OH. It has to be 6, right? We started with the 5, and this is the base. HO and H. No difference, right? Start from the bottom. This is the same thing because they came from the ribose, arabinose. The arabinose are the same thing. Now this aldehyde group converted into hydroxyl group, right? CHOH. And now one hydroxyl group on the right, H, and another hydroxyl group on the left. Please once again, pardon me, my cursor again. So hydroxyl group on the left. And that's basically 2 isomers, stereoisomers, right? So now we got to start with the pentose, arabinose, we ended with 2 molecules. And base remains the same. And the 2 molecules, one is the carbon number 2, hydroxyl group on the right, carbon number 2 on the other one, carbon on the left. So which one is the right? Hydroxyl group right, it is called D-glucose. The molecule is called D-glucose. D-L-U-C-O-S-E. Glucose. Glucose. All right? D-glucose. D, just a G. Please make sure it's a G, okay? It has a abbreviation, it's called DGLC. That's a 3-letter abbreviation of the glucose, GLC. All right? So that's a D-glucose. And other one is D-mannose. M-A-N-N-O-S-E. Mannose.
I forgot it.
Yes?
So does D-mannose have 2 hydroxyl groups on the left side?
Yeah, well, absolutely. Yeah, 2 hydrogen on the left hand side, and the glucose is alternative. Hydroxyl group on the left, hydroxyl group on the right. It's alternative.
Why is that?
Because it started with the arabinose. Look at the arabinose structure. This is the arabinose structure. That's the base of the arabinose. That's the base. So arabinose has CH2OH, CH2OH, OH,
Okay.
OH, OH, and OH in the left, OH in the left. Same thing.
So
D-glucose is the same thing. OH, OH, and OH. So the base of it came from arabinose, so the base structure remains the same. Only the aldehyde group converted to CHOH. Yeah.
Okay, so you did not, you weren't showing the reactions of D-ribose as well. You were just showing D-arabinose.
D-arabinose. D-ribose, you're done. D-ribose, you're done. Let's put this way. Yeah. D-arabinose is going into these 2 molecules. Yeah. And D-ribose, we're not going to go further. This is good enough because they have applications right here. D-arabinose has to convert it to hexoses. 2 hexoses. One is called D-mannose and one is called D-glucose, both are our food particles. Remember, whatever we do, the carbohydrate we take, it goes inside the stomach, hydrolyzed, and ultimately it will become glucose. Glucose will go inside the cell, go to the glycolysis, it's a cycle, electron transport chain, get ATP. Mannose does the same thing. If we have a mannose in our diet, it will do exactly the same thing. So it will go to glycolysis, TCA cycle, and electron transport chain to generate ATP. So these are the hexoses. So make sure you remember the structure of D-ribose. D-ribose is also known as D-rib. The three-letter abbreviation is called D-rib. All right, not the rib cage, huh? D-rib. D-rib, and this is the D-deoxyrib. D-deoxyrib. So these are three-letter abbreviation, okay? But this is the deoxy, you have to write it again, but D-deoxyrib. All right, so that's basically so you must know the structure of these four of them. D-mannose, D-glucose, D-ribose, D-deoxyribose. Now, who can tell me what's the difference, the configurational difference between the D-mannose and D-glucose? What's the difference? Let's say I'm going to write the carbon number 1, carbon number 6, and carbon number 6. Tell me what's the difference between these two molecules, D-mannose and D-glucose? What's the difference in terms of the configuration?
On carbon number 2, the hydroxide group is on the left for mannose, and then on the right.
Excellent point. Yep. So they are called 2 epimers. 2 epimers. Yeah, excellent point. They are called 2 epimers. Why 2? The carbon number 2. So the configuration of the hydroxyl group in the carbon number 2 are different. So therefore, D-glucose and D-mannose are called 2 epimers. 2 epimers.
I have a question.
Yeah.
So how does it switch? So do you go from D-ribose to D-glucose? And I get that. Does that a reaction for those three? And then how do you get from the D-mannose? Because they're just added. There's no reaction.
So
I'm
you have a reaction 1, 2, and 3. So whenever you take one molecule from this, you'll end up with the 2 molecules right here. One molecule ended up with the 2 molecules. Always 50-50, 50%, 50%. Yeah.
Okay. Thank you.
Because CN minus can attack from this side or can attack from this side. Depending on the attack, they'll make 50-50. Yeah. Now, one more, the last one is the D-thiose. D-thiose, we're writing the reaction 1, 2, and 3. It is a 4 molecule, 1, 2, 3, 4. We'll do 2 times. We'll do 2 times of this reaction, and we'll end up with a molecule like this. I'm going to give the structure only. I'm not going to show you all those isomers. There are plenty of stereoisomers will be there. And just please write it down right here. Carbon number 1, 2, 3, 4, 5, and the 6. Because we did 2 times, right? So carbon number 6, CH2, OH. OH. All right? It remains the same. And it's coming for the base right here. So 1H this side, 1H this side, hydroxyl group on the left, and H. All right?
I gotta ask you a question.
Yeah.
I just never got it of like when you put the lines at like 6, is it because carbon have 6 electrons or it has nothing to do with it?
No, this middle, the joint of these lines, the carbon. Carbon has 4 bonds always. It can have 4 bonds always.
Okay, so that's why it's 4 lines.
That's a 4 lines.
Okay, that makes sense. Thank you.
You're welcome. All right. Now, I'm going to write the structure, and I'm going to give the name also, and you are going to tell me what's the difference between this and glucose. This molecule is called D-galactose. D-galactose. Please write down D-galactose or D-gal. Gal for galactose. Letter abbreviation. Now, what's the difference between the glucose? Glucose is right here. Please compare glucose and galactose. Who can tell me what's the difference between glucose and galactose? One gentleman told me the 2-epimer. Please look at, or anyone, please take a look at it very carefully and tell me what's the difference between the glucose and the galactose. Please tell me. I'm going to wait for it. So DGLC and D-gal. What's the difference between these? What's the difference between these? And because of that, they have a relationship. D-gal, this is GL, huh? DL. So D-glucose and D-galactose, what's the difference between the structural configuration? Anyone?
Galactose has 2 hydroxide groups on one side.
Which carbon we're talking about? You have to go carbon by carbon. You have
2
to go
and
carbon.
3.
Huh?
2 and 3.
No. No.
It's switched on carbon number 4.
Ah, excellent point. So that's why D-glucose and D-galactose are known as 4 epimers. Yeah, excellent observation. Yes. So D-glucose and D-galactose are known as 4 epimers. D-glucose and D-mannose are known as 2 epimers. That's a relationship between those two. Yes. Tell me if you have any question. These are the molecules that you must know the structure. The mannose, the glucose, the ribose, the deoxyribose, and the galactose. The galactose is also our food particle. If you take a lactose, the milk, plenty of it, lactose there, the lactose will be converted to, will break it down to galactose and glucose. That galactose will go inside the cell, glycolysis, TCA cycle, electron transport chain, generate ATP. So basically, D-mannose, D-glucose, D-galactose are food particles. D-ribose, deoxyribose are the components of RNA and DNA. Very important part. Everything is important, right? So D-mannose, D-glucose, D-galactose are the food particles. Our food. Do you have any question on this one?
I have a
Yes.
question.
Yeah.
So, what you have an arrow going from D-ferrose to D-galactose. Is that directly from it because it has 2 extra groups?
So D-thiose has 4 carbon. 1, 2, 3, 4, right? Yeah. 1, 2, 3, 4.
Yeah.
You do the reaction 2 times. You get many molecules, but you are not. I'm not going to write molecules. You get many. Every time you do the reaction, you get 2. Every time you get the reaction, you get 2. You get many. Yeah. One of the molecule is D-galactose. Yeah. Any other questions?
Okay, so I have a question. So for D-galactose, for the, let's say the 4th line, they like switched. So would that make it like 5 emmers?
Please say it again. I think I'm. Say it again.
Okay, so for when you had the difference between galactose.
So D-galactose and glucose that we are comparing. We are comparing this structure
Yes. So
and this.
So when you said 4, you said like for the 4th bond, they traded between hydroxide and hydrogen for the 4th carbon bond, carbon 4.
Mhm.
Okay, so what if the line below it nitrate. That's what I was referring to. Because
Which one? Which one?
bond at the bottom is the same for D-glucose.
So D-glucose, you have a carbon number 6 CH2OH, right?
Mhm.
Carbon number 6 here, CH2OH. Carbon number 5 HOH. Carbon number 5 HOH. Carbon number 4 HOH. Carbon number 4 OH and H. So that's the difference. So this is C4 has a hydroxyl group on the left hand side of galactose, and C A, what is called in the glucose has hydrogen on the left hand side. So that's the configuration difference in C4. So that's what they call 4 epimers. 4 epimers. 4 epimers. Yes?
Is it
Yeah.
called 4 because it's on the 4th carbon?
It is a 4th carbon. That is correct. Because the 4th carbon coordinated. Yep.
Can you repeat the sentence we need to know the structure of again?
Huh? Say it again.
Can you repeat the names that we need to know the structure of again?
D-mannose, D-glucose, D-galactose. That's a hexoses. D-ribose and deoxyribose. And the relationship and the replications. I already told you about applications, right?
Thank you.
You're welcome. Next one is the carbohydrates ketoses. Go down with aldoses. Precursor of ketoses is dihydroxyacetone. Dihydroxyacetone. So, if you start with the glycerol, remember the glycerol structure, right? I gave you earlier. CH2OH, that's a carbon number 1. Carbon number 2, CHOH, and it's a D. Always in the D, right hand side, hydroxyl group right hand side, and the CH2OH. All right? OH. That's our glycerol. Carbon number 1, 2, and carbon number 3. Now, when we made the glyceraldehyde, we did the limited oxidation at C1 carbon. Now, we're going to the glycerol after limited oxidation, the C2 carbon, carbon number 2. So, plus oxygen. And since the limited oxidation, we have to have a catalyst. Cat, not the cat, I'm writing cat in short, not the man, it's a catalyst, CAT. All right? Catalyst, and it will be converted to carbon number 2 is oxidized now. It's a limited oxidation, selective oxidation. OH. And if you oxidize the secondary alcohol, what do you get? Do you remember? You have to get the ketone. If you oxidize the primary alcohol, you get the aldehyde. That's a glyceraldehyde. That's a C1. And if you oxidize the secondary alcohol, that's a secondary alcohol, right? It's R group CH. R1 or RR CHOH. Secondary alcohol oxidized to keto group. This is called DA, dihydroxy acetone. You know the formula of acetone, right? CH3, CO, C double CH3. Replace the one hydrogen with the hydroxyl group from both CH3, CH2OH, CH2OH. It's called dihydroxy acetone. That's the name. DA, dihydroxy acetone. That's our DA, right? And it is not a D configuration, right? This was a D. This is glyceraldehyde, right? But it is not optically active, right? Because you have a CH2OH, both are the same, and it is converted to keto group. This is not optically active center because it is a double bond. So chirality, none. No chirality. All right? And now this molecule can be subjected to the same reaction. Number 1, 2, and 3. Remember, every time you do the reaction sequence 1, 2, and 3, you add 1 carbon. And where will you add it? Carbon? The carbonyl carbon. Because this is the nucleophilic center. So Cn minus will attack right here. So Cn minus usually attack right on this carbon now. It can attack both sides, on this side and this side. And either side it attacks. If it attacks from this side, hydroxyl group will be right. If it attacks from this side, hydroxyl group on the left. And let's do the reaction. This is carbon number 3, right? 1, 2, and 3. Let's do 3 times. So you'll get many, many molecules. You do not have to know all those molecules. But the molecules that you must know is this guy. You have to know the structure of this one. And I tell you what. Class is over?
Yeah.
Yeah. Do you think I have a time to draw this one or not? Maybe?
Sadly, I don't think so.
I don't think so. You're not going to give me another few seconds? 1, 2, 3, 4. Right? 5. And this. Give me 1. Not 1, 10 seconds. This. H, because I'm already too close. This and this. All right. And HOH. That's it. So this is the molecule, the structure you must know. Why? It's called D-fructose. If you recall, fructose is one of our food particles. D-fructose or DFRUC.